Thank you so much for that introduction, Tavy. Here's first want to make sure everyone can hear me and see my laser pointer here. Unless there's any problems there, I'll just get going. And I want to say I feel really privileged to give this seminar series, give an overview of the work that I've been working on here at LPL for my PhD research. And of course, that goes without saying that this, oh, see, that didn't transfer over. Let's get these slides going. Okay. So all of this work has really been made possible by a huge team of co-authors. I've been lucky enough to publish a couple of papers on our research so far. So I'll talk a little bit about our data acquisition up to date. And then on the left there, you can see a big list of names there. And each of those people have personally helped either assisting in the field work and holding the transmitter and receiver of the GPR that has collected the data or typed some of the code that has gone into the analysis. So just a huge amount of gratitude for my team and co-authors and field crew. So without further ado, I'll start talking about let's see, it doesn't like when I do it. There we go. Okay, figured out the slide issue. So I'll address the elephant in the room. Obviously, I'm sitting here in Arizona, which does not evoke thoughts of glaciers in a typical mind. But actually, I have a picture here of the U of A campus. I'm sitting right here in this building, and we're looking in the background towards the Catalina Mountains, which you can just see a little dusting of snow there. So that's a little hint that even here in the desert, we really care a lot, or even more, about our allocation of water resources and characterizing the distribution of water for both understanding the climate patterns as well as understanding water resources that are extremely important to human life. And along that same vein, in this same building that I'm currently sitting in, just in the floor above me, is this replica of a very large camera, which the real camera is currently orbiting Mars on the Mars Reconnaissance Orbiter now, and that's the HiRISE camera, which is the High Resolution Imaging Science Experiment, which is the highest resolution camera we have that's orbiting a planet other than Earth right now. So those operations are based out of the U of A. So with all of that together, with the focus on planetary sciences here at Arizona, it is a great place to be studying Martian glaciology and the analogous processes that occur both on Earth and Mars. Let's see. So here I just have a quick little globe inset showing a topographic hillshade of Mars. You can see the famous Valles Marineris Canyon here close to the equator of Mars. But I want to draw your attention to these orange and green bands that I've highlighted along the mid-latitudes of Mars. And those are all mapped ice deposits. So the orange is mapped debris-covered glaciers in the mid-latitudes of Mars. And the green is essentially a consistency value from the subsurface water ice mapping project, or the SWIM project of Mars. So up to this point, all throughout the mid-latitudes of Mars, there's a huge amount of debris-covered glaciers that have been mapped, but there's a lot of details that have not been understood thus far. So here's a little zoom in just of an example of a specimen of one of these Martian debris-covered glaciers. This is in the southern mid-latitudes on a mountain called Europus Mons. So here we can see a very low bait and flow reminiscent morphology. So we can see this arcuate ridge morphology accentuated by some sharper ridges that are deforming downslope here. And we actually also have radar sounding evidence on the same spacecraft as the HiRISE instrument. We have a shallow radar sounder, or SHARAD, and that has actually detected the base of these debris-covered glaciers in the mid-latitudes of Mars. And this plot on the right here is an overview of the detection of those glacier bases on Mars. So essentially, what happens is the radar signal detects this basal reflection here at the base of the debris-covered glacier. And it's important to simulate the surface clutter, or the off-nadir reflections that are essentially reflecting on the topography off to the sides of the track of the spacecraft. And by qualitatively comparing the locations of the reflections and ensuring that there's an absence of clutter in that travel time location, then we can infer that we are actually detecting the base of the debris-covered glacier. And then by fitting in this depth-corrected radargram, by fitting this basal slope to the background topography, that gives us an estimate of the dielectric constant of the debris-covered glacier, which is very consistent with relatively high purity water ice. So that's the background information we're starting off with on Mars. So we already know that there's these huge debris-covered glaciers that have a relatively high water ice content on them. Need to get used to this. There we go. So this has implications for climate history as we map out the stratigraphy and potential surface morphology patterns on these debris-covered glaciers. So we're really interested in characterizing the overall Martian climate history, as well as understanding the mass wasting and debris transport rates. And that can help us also give us a clue into the climate history and the variations of weathering throughout the Amazonian period of Mars, especially. And then, of course, human exploration remains of interest to a lot of people moving into the future. And of course, water is a vital resource for any sort of human settlement or exploration, or any long-term sorts of living scenarios. So those are our main motivations for understanding Martian debris-covered glaciers. But the best way for understanding the debris-covered glaciers on Mars in an absence of higher resolution data is to compare these features with analogous features on Earth. So that's where we come into this debate of the debris-covered glacier and rock glacier continuum. So I wanted to talk about this too a little bit to begin with, just to address maybe a smaller elephant in the room, that these features may originate from fundamentally different processes. So I just wanted to call attention to this awesome review paper by Anderson et al. that came out in 2018 that covers the continuum of debris-covered glaciers and rock glaciers, and including clean ice glaciers in there. And it does a really nice job showing some of the dynamic modeling and the impacts that this rockfall and superglacial debris input can have on the overall length and lifespan of a debris-covered glacier. So essentially, we're working with two end-member scenarios of this continuum, where debris-covered glaciers are purely glacial origin. The ice has never melted and the original stratigraphy is in place. The debris layer is relatively thin, and there may be some entrained debris layers due to oscillating ice mass balance that can bury superglacial debris layers, whereas rock glaciers are considered to be more of periglacial features that have been infiltrated by freezing and thawing ice over and over again. And this tends to create thicker debris with interstitial ice, or sometimes some deep discontinuous ice cores. So in reality, we really observe different features that occur on this continuum that may be influenced by both glacial and periglacial processes in the same valley system. So some of the parameters that may influence these evolutional differences are valley geometry, so things like the cirque parameter and the accumulation area, the head wall erosion rate, and then environmental factors that can also change over time, such as the local equilibrium line altitude. And then I just pulled this animation from that review paper that is a really nice example showing what these showing the transition between debris covered glaciers and rock glaciers with an oscillating air temperature over a 1,000-year period. Although it's now my cursor is struggling to. There we go. So as you can see, it oscillates between a longer debris covered glacier, and you can see this end glacial debris band develop as the debris covered glacier grows, and then it retreats as the climate warms, and the debris thickness is concentrated on top of this rock glacier. And then on the bottom part of the plot, you can actually see a progression of a ground moraine where that debris is then deposited from melting ice. So this is a really nice holistic model showing the transitions between rock glaciers and debris covered glaciers. So for the purpose of this talk, I'm going to use rock glacier interchangeably with both cases, just because it's fewer syllables and it encompasses this entire debris covered glacier rock glacier continuum. Okay. Oops. Next slide. Okay, so my guiding questions on both Earth and Mars for this research. Essentially, the first question is just how much subsurface ice is there? What is the total fraction of ice and rock in each of these features? And what are the processes that are comparable between both Earth and Mars for debris covered glacier, rock glacier evolution? And what can we infer from the stratigraphy and the surface morphology of these rock glaciers about the climate history? And I even do a couple of tests about how the lithic fraction in the rock and debris inclusion impacts the ice rheology. And then this research will help us define some of the important measurements that we want to collect in the future for monitoring rock glacier change on Earth, and then also planning future observations of debris covered glaciers on Mars. Okay, so I'll give a quick outline of what my research will be showing here in this presentation. So I'll just start off with data acquisition and show 3D reconstruction of each of our rock glacier field sites. So we'll use ground penetrating radar and airborne photogrammetry to get a 3D view of each study site. And then I'll go into the analyses that I apply all of those data sets in this combined kinematic and dynamics analysis. And then at the very end, I'll go back to Mars and take a look at some case studies in light of what we've learned with this study here. Okay, so just to introduce you to our terrestrial study sites. So we have two pairs of rock glaciers here, which is really exciting because it gives us a natural laboratory to test both regional and local variations in the factors that impact rock glacier evolution. So you can see our Wyoming site here. We have Galena Creek Rock Glacier, which is one of the most well-studied rock glaciers, definitely in North America and even in the world. And that's really thanks to Noel Potter Jr. and his work going back to the 1960s, where he started characterizing boulder positions and making some of the first geomorphic observations at that Galena Creek site. And it also is only a couple of kilometers away from Sulphur Creek Rock Glacier over here to the southeast, which is overall a much larger feature. a little bit harder to access, so there's less historical data going back. But we did collect some photogrammetry and some GPR data at Sulphur Creek as well. And then we have a pair of rock glaciers in the Wrangell Mountains of Southeast Alaska. The southernmost one is Sourdough Rock Glacier here, flowing down the southern face of Sourdough Peak. That one is fairly accessible from the toe. You can hike up onto it. So we were able to get some GPR data there, as well as some airborne photogrammetry. And then McCarthy Creek up on the other side of the ridge of Sourdough Peak, we weren't able to access it on foot, so we only have the airborne photogrammetry data there. But we're still able to make some really interesting comparisons between the two. So those are the two pairs of study sites we'll be looking at, and especially Galena Creek. That's kind of the type example of this rock glacier continuum that we're looking at. Oops, sorry. So we'll start off with the ground penetrating radar portion of the acquisition. So this is a really common method in glaciology overall, and even with rock glaciers, the table on the right there shows probably a non-exhaustive list now. I know there's more studies out there that have used GPR on rock glaciers to measure their wave speed and subsequently their dielectric properties and ice composition. So you can see it's an extremely common method for measuring the geometry of glacial deposits, solely for the reason that radio waves propagate very well through ice, and it's one of the best media for radio waves. So one of the most important parameters to consider when measuring thicknesses via radar is the radio wave speed, because really when we're doing a radar survey, we are transmitting a radio signal from a transmitter, which we have right here in the picture. And that is being transmitted into the subsurface, where it'll reflect off a dielectric interface and then be received at this receiving antenna over some given time interval. And by measuring that time interval and assuming or measuring a velocity of the radio wave in that medium, we can actually estimate the thickness of that feature that we're measuring. So we've used a couple of different methods on our rock glacier field sites. We went out to Alaska in the winter one year and dragged our pulse echo system on a sled. But we found a little more consistent success, even though it's a little bit slower. The ability to consistently collect traces with this manual method, kind of with a bigger team, is the most efficient way we found, at least for the surface-based GPR. So that is just a good testament to how important the teamwork is in this case as well. So the way that we measure our thickness and composition using ground penetrating radar, we're actually going to use two different antenna configurations, and those are the common offset configuration and the common midpoint configuration. And that describes the alignment of each of the transmitting and receiving antennas. So the common offset essentially creates a subsurface cross-section of the medium, and then the common midpoint profile actually moves the antennas outwards and provides a geometric estimate of the wave speed, because by increasing the distance that the wave has to travel and measuring that increase in travel time, it's a direct geometric measurement of the velocity. So both of these geometric scenarios are governed by these relatively simple geometric equations. But one thing you'll notice is that if you introduce this dipping reflector angle theta into the equation, that will actually change the travel path and the travel distance of that radio wave. So if you assume it's a flat reflector, you're actually going to overestimate your velocity because it decreases your travel path, as you can see by this example here. So if you don't account for your reflector dip, that's going to overestimate your radio wave velocity, which will then give you an overestimate on your depth. And it might even give you a value for your velocity that doesn't make sense if it gives you a value that's too high to be feasible for pure ice. And then here's just a quick sneak peek of a future radargram, but you can see that there's just a ton of dipping reflectors in some rock glaciers. They've been documented in several sites around the world. So this just shows that it's really important to account for that reflector dip when you're correcting for that radial wave speed. So the way we make that correction is to treat these two governing geometric equations just as a simple system of equations, really, and that's represented in this plot down here, where this black line represents the common midpoint hyperbola equation, and this red line represents the common offset equation, and the intersection point represents the best fit velocity and dip angle that's consistent with both configurations of data. So here's an example. This is an example from sourdough where the base is relatively flat here. There's only about a 3-degree dip of that reflector. And then if we move to this Galena Creek example, this shows what happens when you need to make that dipping reflector correction, because initially, if you don't account for that reflection or that dip, then the velocity is above 0.18 meters per nanosecond, while we know that the highest value that we expect from ice, compacted ice and not snow or anything like that. So we know it shouldn't go above about 0.17, and only by applying that dipping reflector correction do we bring it back into this physical value. And it's also consistent with this relatively reflection-free zone. So we're still getting close to a high ice purity in this case. So then when we have these velocities in hand, we can then go and apply those to our travel time measurements for all of our common offset profiles. And that gives us these thickness maps across the glacier here. So we want to keep this thickness map in mind here for Galena Creek. And then we can also map out the distribution of radio wave velocities, and then applying those velocities to a dielectric mixing model here at the bottom left, that assuming the dielectric constant of rock is about 9 and the dielectric constant of ice is around 3, this gives us an estimate for the ice and rock fraction for that measured velocity value. So by plotting each of our study sites along this plot, then we show our relationship between our measured velocity and ice fraction. So in doing this system of equations method where we combine our antenna configurations, that gives us a more confident estimate of both the geometry and the composition of our rock glaciers. So now I'll move on to the 2D surface motion measurement here. So what we do with our photogrammetric change detection is we want to repeat our overpasses with our airborne flights, whether that's by a drone, which I have pictured here is kind of the most dramatic version, or the most dramatic moment in this acquisition is making sure the drone doesn't crash when you're landing it. So we can fly a drone that has these really high resolution, high precision images that can then be combined into an orthomosaic and the DEM from structure from motion processing. And we also combined that with some piloted airborne flights at our Alaska sites. And we also acquired some satellite imagery from a company called SOAR, and they were distributing SkyMap 50 images at about 50 centimeters per pixel. So we used a few of those to get some more time samples. And by using these repeated images and a feature tracking algorithm, we measured the surface velocity of our 4 field sites that I outlined. And as you can see at the bottom here, one of the main challenges of this method is the fact that rock glaciers move much slower than your typical large ice stream or marine terminating glacier that you may have seen videos of, like Landsat time lapses that you can detect the motion in there. These don't move nearly as fast, so you need much higher resolution, high precision imagery to detect these movements. And this figure right here is just a good example of the number of images that are collected for each survey, and then the overlapping images are what are used in the structure from motion processing to create our DBMs. So this is just a quick overview of all of the images that we processed. So you can see there's a ton of combinations that we can measure the displacement between these image pairs. And just a quick shout out to Chris Larson, who was the pilot. Every single one of these Alaskan flights was a piloted overflight flown by Chris. And then our Wyoming site was a little more varied, where we had a few UAV flights, one piloted overflight, and then we also acquired a few of those SkyMap images to piece together our displacement time series. And it also just gives a good example of the range of resolutions and the number of images we collected. And then this year, the table didn't have this year's acquisitions, but this past year we were able to collect a drone image at Sulphur Creek, which was a first for us. And I just want to highlight that it took 9 batteries of the UAV. So that was another huge effort by the whole team to get that entire orthomosaic flown in one day. So that was really awesome. So this will hopefully just give you an idea of the data volume and the sort of the parameters that can be expected from these types of UAV photogrammetry flights. So really this almost 4 square kilometers in a day was the upper limit. Oops. Okay, so here is a look at what the results look like when we do this feature tracking. This schematic here in the upper left shows an example of how the change detection algorithm works. I used this correlation image analysis software that's freely online from the University of Oslo. And what it does is you specify this reference block, which I've shown here in red, and a search window in blue. And it will take the pixel block within this reference block, and then it'll search the second image within the search window. And all it does is take the normalized cross correlation of the pixel block throughout the search window. And wherever the maximized normalized cross correlation is, that is where it maps the displacement. So the displacement being between the reference block in the first image and the second image is our displacement vector, which we then convert to velocity just based on the time interval between the images. So we have our plots here. The way I've chosen to plot them is I show the vector magnitude in color, and then you can see the direction plotted as the orientation of this line plot along the map. So we have this 5 meter by 5 meter grid that I've ran this change detection algorithm on. And overall, we get an excellent signal here at Galena Creek. This is the 2020 to 2023 image pair. So this is a 3-year time interval. And overall, we see this really nice flow band correlating with this main glacial flow channel. And also highlight here, we have a region of elevated velocity there, and then one more here. And those, it's probably easier to tell if you've been there hiking, but these these elevated regions correspond strongly with surface slope. So we are observing the glacier speed up and slow down as it flows over nick points in the bedrock. And that'll be important a little bit later. And then also this first image of Sulphur Creek, or this is the first drone-based change detection result that we've been able to show for Sulphur Creek. And what we found is kind of surprising, or at least striking, in that we have this elevated velocity in the middle here, but if you look closely, the directions are actually flowing towards the middle of the glacier and not towards the terminus. So when we look at the elevation data, we'll see a similar pattern, but what we're interpreting here is that there's an enhanced amount of melt within this central section of Sulphur Creek Rock Glacier, which is actually leading to a destabilization, and the glacier is collapsing inwards, which we're detecting in this upper part of Sulphur Creek. Whereas getting down below this break in slope, this is the lower portion where there's less ice, and we've measured a lower radial wave speed down here, but it's actually more active and seems to be actually accelerating towards the terminus. So this could be indicative that this whole Sulphur Creek system is right at a tipping point, possibly due to its increased accumulation area in relation to its cirque perimeter. So that's just an example of the local variations between these two rock glacier field sites. Even though they're really close to each other, they're clearly changing in very different ways even today. And then over here, I just have a few quick numbers showing the overall uncertainty of these displacement values. And the main thing to show is that this mean displacement is on the order of about 5 centimeters. So that's what we're taking as our limit of detection or uncertainty, barring any of these noisy pixels, which are essentially a result of mismatched reference blocks and search windows, possibly from shadows or trees. But overall, our baseline uncertainty of 5 centimeters is excellent for measuring even these displacements, which we've seen up to about 1.5 meters per year when you divide the displacements by the travel times. Okay, and then just really quickly to show the results at Sourdough, since we have way more images, we tried to do a time series to see if we could find any seasonal or annual signals. But it turns out the displacements over single years or even single seasons are just too small to confidently interpret any definitive signals in the data. But we are getting consistent results in that this central trunk section approaches about 1.5 to 1.8 meters per year. And you know, the quality of these change detection results also varies. So you can see this one has a really smooth character to it and a nice flow signal flowing down the whole trunk of the glacier, whereas this one right next to it, there's actually a tiny bit of snow in these images. So you can see any sort of effect that can lead to a decrease in pixel correlation will negatively impact this algorithm. And then for comparison, we also did this McCarthy Creek, Alaska site where we actually tried to measure the displacement from a single base image over this August 2014 base with similar results as the annual intervals on Sourdough. And it really does depend on image positioning quality and the time interval. And the main thing to note from McCarthy Creek is that we're seeing a peak velocity that's around half that of Sourdough, despite the fact that they're right next to each other and they have similar surface slopes. So that tells us that there may be something different about their rheology, maybe their internal temperature. I thought that was a really interesting result that despite the fact that they're right next to each other, we see similar results as far as image quality, but the peak velocity of McCarthy Creek is about half of Sourdough. So to add on to our results of surface change, we can also measure vertical surface change. And all I did for that method was to subtract our 2023 DEM from our 2020 DEM, and that gives us an elevation change profile. And one thing that's obvious in this sort of first order estimation is that there is a lot of bias off the sides of the glacier. On this stable ground, you'll see it's all still red. So that means there is some negative bias, which we can also see just by this baseline in the plot on the profile that I've plotted here. But we can observe that the mean of this on glacier DEM difference is about twice the amplitude of the mean of the off glacier DEM difference, and the variation on glacier is also greater. So we can infer that there is some real effect on the elevation change occurring on Galena Creek Rock Glacier, in that it's thinning. It's not the same as the stable points around it. So perhaps higher order analyses could add certainty to these estimates. But in general, our estimate of about 20 centimeters of elevation loss over those 3 years are consistent with previous estimates from geodetic measurements presented by Noel Potter in 2016 at GSA. And then to use the same method over at Sulphur Creek, we leveraged a DEM from the USGS that comes from this 1985 topography data set. And then we also are able to do a shorter time interval change between 2020 and 2023. And the results are similar in that both off glacier stable ground regions are biased, but on glacier, we do see a signal that appears to exceed the bias off glacier, which we're interpreting as this enhanced melt signal, which this region right here in the middle of Sulphur Creek, that is consistent with the area in the horizontal change detection that we saw was actually collapsing inwards. And then these red regions up here actually are snowfields that don't have debris on them because they haven't had time to develop a debris layer. So those are just open to the sun and are melting even faster than the rest of the glacier in both those data sets. And a curious thing is that we didn't actually observe any elevation changes outside of the uncertainty and bias in the Alaskan data sets. So only in Wyoming is where we saw this rapid melt signal. Okay, so now we have our 3D glacier thickness, composition, and surface motion. So now in the next 10 minutes, I'll run through some of the methods I've been using to analyze these data sets and how that is wrapping up into my dissertation for this semester. So we want to figure out maybe what's the total age of these rock glaciers, how can we infer climate oscillations, and also can we interpret these arcuate ridges on the surface that are so common on rock glaciers, but can we actually figure out how they were formed? So first of all, I applied just a really simple analysis to these flow fields. So all you have to do to get these kinematic ages of each of these rock glaciers is you take in a long flow profile. And so we have the speed here in blue, and this profile shows the along flow transect along Galena Creek. And all you have to do is integrate that profile. So basically add up how long the point on that surface would have taken, assuming the same velocity field. uh, how long would it take to go from the head wall to that point? And then if we do that all the way to the terminus, we get essentially an age of flow of this rock glacier feature. So we did this at Galena Creek, and the terminus age is consistent with this value a little bit over 3,000 years, which is consistent with an accumulation starting sort of in the mid Holocene, this kind of neoglacial accumulation period. And what's really convenient is that there exist these radiocarbon ages from this Conrad et al. Paper from different points along the rock glacier at this site. And we were able to validate those locations, and it's just really nice that our ages fell within the error bars of the radiocarbon ages that were measured in leaf fragments at similar points along the rock glacier. So then Sourdough gives a similar age as Galena Creek, sort of this mid-Holocene. But then McCarthy Creek, as we mentioned, it's about half the speed, which when you're just integrating that velocity field over the entire length, that then translates to about double the age. So this gives more of sort of like an early Holocene type age. So that is another indication that even though they're right next to each other, these rock glaciers do have differences and they evolve differently. And there's still a lot of work to be done to figure out exactly why they are evolving so differently. But we're just starting to figure out some of the hypotheses we want to explore. So then using that same concept of integrating these ages over the length of the glacier, we can take these internal layers and the locations where they outcrop on the surface. This is the radargram I showed you before. And we take the distance downflow of each of these outcropping locations. And we can actually assign a specific year that this surface is correlated with. And if we assume that that's an internal debris band correlated with low ice mass balance that allowed a debris layer to form, then this gives us a first step towards interpreting climate signals and periods of low ice mass balance during this little ice age period that's represented in this upper region of Galena Creek. Okay, so this is kind of the main result that I wanted to get to and show you all, is that if we calculate the strain rates from our surface velocity data, we can use these strain rate tensor components to make comparisons with the occurrence of different surface features and glacier deformation. So all you have to do is take the gradients of the velocity components with respect to the different horizontal directions. So this will give you these three tensor component plots with the XX longitudinal strain rate and then YY. And then this one on the right shows the shear strain. And then I'll just zoom in a little bit to show a better view here. So what I noticed when I mapped out these strain rates, and one thing I should mention how to read these maps. Essentially, blue is a positive value, which corresponds to extension or this sinistral strike slip motion, and then red is the opposite. It essentially correlates to compression on longitudinal plots. So when I plotted the locations that we had mapped out in the field where there's ice exposures and sub-debris melt, we actually see that all these locations plot perfectly with these lineations within the cross-flow XX strain rate. So where we see these ice exposures where we assume there's enhanced melt, we actually see the glacier is also slightly moving inwards, where there's this enhanced melt and slumping motion essentially. So this could be a great way to map out candidate melt streams where they flow beneath the debris layer. They're not on top of the debris, so you can only hear them or see the ice when it fully incisors through. So that was a really cool result. Is that there's this clear correlation between cross flow compression and enhanced melt. And then I want to draw your attention to this YY along flow strain rate map. And especially in this area right here, we see a quick succession of blue, which means extension. Whoops, sorry. And then red, which means compression. So when we're moving down flow here, and then I've also plotted a GPR debris thickness profile along this transect here. So what you'll notice is that as we move along this flow direction and we hit this strong blue here, which indicates a rapid extension of the surface, and then immediately the GPR line here, it thins. So what we're inferring is that the extension of the glacier is actively pulling apart the debris layer. And what that does is it decreases the thickness of the debris layer, which then decreases the impedance to thermal conduction towards the ice, which will then allow for faster melt. So we also see one of the main ice exposures we've returned to is also right next to this area of rapid extension. And then finally, we return to a compressional regime as the surface flattens back out from this steep area. And we see this strong compressional signal. And then all of a sudden, all of these arcuate ridges appear just below this compressional signal. So we're actively observing the formation of these compressional ridges below the compressional signal. So we're directly observing the modifications of the debris layer on or by this rock glacier strain. And by the thinning of the debris, this also impacts the dynamics of the glacier because it increases the melt rate. So here I just wanted to show this map showing my interpretation of the origin of these ridges using a hill-shaded topography map. So I'm interpreting that most of the ridges on Galena Creek are compressional in nature. The only ones that I've interpreted as climatic ridges are these broader ones, which I'll show on the non-annotated version. And those I also only really have confidence in because we have GPR data in them. So those are a little bit harder to infer just from imagery data. So it really takes this holistic understanding of the setting and the topography of the whole glacier system. And one last thing I'll add is that as we see these englacial layers flow down the glacier and all of a sudden they disappear and all of these boulders start to appear, and that's consistent with a increased emergence velocity, which you may recall is essentially represents the relative motion of an internal debris band or an englacial particle with the surface based on its location in the ablation zone. So in this area, when ablation increases and surface slope increases, that will actually drive these englacial particles to the surface, which is why we see so many of these boulders in this one area. So that really answers our question of how can we delineate between compressional ridges and climatic ridges, and why don't we see them continuing further below this area on Galena Creek. So I see I'm running out of time because I just got too excited about all of this, and I'll skip through kind of this more quantitative analytical analysis where I'm essentially trying to best fit our our cross-flow velocity profiles with some analytical uh, streamflow models. And then I've also began doing this numerical simulation with help from Claire Cook to test these scenarios with different bed topography grids. And if you have any questions about the details of those thickness grids, feel free to ask questions, or I'm happy to chat about any of these methods. I've used a few methods that incorporate GPR, but also don't incorporate GPR. And yeah, I'm just happy to chat more about some of the ideas that we're working with. So just to skip through some of these slides, and I'll try and leave some time for questions here. Here, I'll just skip over to Mars really quickly here, because I just wanted to show a quick comparative study of now what we're working with on Mars. So I've highlighted a couple of the most dense regions of debris covered glaciers on Mars. And I've zoomed in on a couple of these areas where we also see just an abundance of these ridges and arcuate surface morphologies, both in the northern and southern hemisphere of Mars. And again, without definitive high resolution GPR data, it's hard to conclude definitively whether or not there are internal layers within these glaciers. You may want to pay attention to some of the 3D Charade work that's coming out in the near future. But as of now, it remains difficult to interpret all of the ridges as definitively climatic versus compressional in origin. But we can start to map out some of the main unconformities between some of the main glacial periods that have been proposed for Mars, especially as it relates to the stratigraphy of the North Polar layered deposit, where we essentially have a large ice cap on top of a more lithic rich basal unit overlain by a more recent accumulation package. So I'll just pop these summary slides up here, and I'll turn it over to the audience for questions. So thank you for listening and for being here.
Thank you very much indeed, Tyler. It might take people a few moments to read your conclusions there, but can ask people if they have questions to indicate on the chat. We usually ask people to just indicate that they've got a question and then unmute and actually ask their question. Roger, you're in there first. Go for it.
Oh, excuse me. Yeah, thanks very much, Tyler. Thank you, Tavy, of course. And yeah, apart from anything else, good luck with the rest of your PhD, if I heard you right. Quick question on your GPR. You showed us the kind of trade-off picture between velocities, ice volume, and so on with CRIM and all the various mixing formula.
Right. Yeah.
Isn't it really a three-component problem, because you've got ice, air, and rock? I just wondered how you handled that potential trade-off.
Yeah. Here, I was trying to find that slide. There it is. Okay.
That's the one. Thank you.
No, you're absolutely correct in that that air is a very important component. And my rationale for this this two-phase mixture is that I'm essentially combining. I'm assuming that the ice is porous and that we can consider the porous ice as one dielectric medium. So I know that's not as rigorous as some of the three-component mixtures that have been proposed. Even some of the work on Mars has actually included some of those three-component mixtures. So yeah, no, that's a completely valid critique. And I'll also add that there's, we've observed melt here too. So really you might want to include water, which will then really decrease your dielectric value or sorry, it'll decrease your velocity and greatly increase your dielectric permittivity. So yeah, no, we are definitely simplifying it. And I think this is a good point to add that one of the main uncertainties in this mixing model is we are assuming a value of 9 for the dielectric of the rock, which also is pretty reasonable based on the literature of igneous rocks, but it could be lower than that essentially. So this gives us basically a upper bound for ice fraction.
Well, think positively. It gives you a lot of flexibility in your answer.
Exactly. Yeah. No, to me, it's all about characterizing uncertainty.
Cool. Thanks very much.
Thank you.
That's great. Thanks, Roger. And I guess you might even throw water into some of those, into that mixture in some locations, not on Mars, though, I suspect.
Yeah, not today.
Anyone else have a question for Tyler? You really had a very impressive array of different techniques there. It seems like you've thrown absolutely everything you can at these glaciers. It's great to see that.
Yeah, no, it's been a wild ride. Yeah, no, I don't have enough time to tell the whole story, but I'm really thankful. I started working with Jack back in Texas. So this is the culmination of 7 years, I think now.
Does anyone else have a question? I don't see anything on the chat, and I didn't see. Hang on, what's this? Diego, go ahead, please.
Yeah, can you hear me?
Yes.
Yeah, thank you very much, Tyler, for your great presentation. It's very cool, and I think there's a lot of effort behind of it to compile GPR data and drone. It's very amazing. So my question is mainly related to could you see some limits between debris covered glacier and raw glaciers with your GPR data?
As far as limits, do you mean like the actual contact or like where they meet?
Yeah, yeah.
Or
Could you split and I mean, could you put a line between this and this is the limit of the transition zone? I don't know, maybe based on velocities or ice content or I don't know.
yeah. Yeah, I think I do have sort of a personal opinion on where I draw the lines. So like this is a good plot to show it. Because personally I consider basically everything below here. So everything that's not Upper Galena and Upper Sulphur, I consider those more to be rock glaciers. So anything that doesn't exhibit like very pure ice value, I would say is more consistent with a rock glacier because there's more of a interstitial ice mixing, lower ice content. So I don't know if that's necessarily a rigorous classification, but for example, like on Galena Creek here, you can see it quickly transitions from this 0.17 very pure ice value, and then we have a break in slope here where we essentially see this debris covered glacier quickly transitioning into a rock glacier. So yeah, I think to answer your question, I would say if something doesn't clearly have like a massive glacial ice unit below relatively thin debris, then I'd say it's more of a rock glacier than a debris covered glacier.
Yeah, okay, thank you. It's just a quick comment because if we were faced to the same problem last year regarding the debris covered glacier and raw glacier transition in the French Alps. So it was quite difficult for us to put limits because when you want to calculate, for example, surface mass balance, it's quite complicated to estimate them if you don't discriminate well the features. Yeah. And yes, for example, we made some estimations on supermass balance on rock glacier, and we found more or less the same observation as you. So I will for sure contact you in later.
Yeah, please do. I'd love
Yeah.
to chat more about it.
Thank you very much for a nice presentation.
Thank you. Appreciate it.
Frank, go ahead, please.
Yeah, thank you very much. I actually will now not make my standard statement about the percentage of glaciers to rock glaciers with this transition and the amount of rock glaciers which have never been in contact with any glacier. But because of this nice example here, my question would be, have you considered that maybe the rock glacier part and the glacier part had never been in touch, so that they developed independently? Because there are lots of pure rock glaciers around in this region, so there were likely no glacier at all at any time. And basically also at this elevation for this lower rock glacier parts. So for your calculations of the time of development, it might be interesting to consider that it is actually not a continuous transition from the highest to the lowest point all the distance, but just the lower part that has then developed, maybe without any glacier ice feeding into it at any point in time.
Right. Yeah, no, that's a great point, and I think is a central part of the, I guess, the argument between calling them the same thing versus different things, or even existing on a continuum is like you said, whether or not they evolved completely separately. And my thought in these cases is that all of these areas, both in Wyoming and Alaska, they do have signs of significant glaciation. So at least as far as these specific features, I have been interpreting them as being rock glaciers influenced by debris-covered glaciers. But I do agree with your point that the age estimation is dependent on this constant velocity field throughout time. And one of the things that I've thought about with the numerical modeling that I'm hoping to work on a little bit more before I have to wrap it all up is to explore how the rheology of that ice poor rock glacier compares with the ice rich debris covered glacier, and how that may have changed the velocity field over time. So yeah, I completely agree with your point that there have been rock glaciers observed without any glacial influence. That off the top of my head, I can think of some in North America. But my interpretation is that in this case there has been some amount of glacial influence in all of these locations. But the Alaskan sites, I would say, are more.
I don't think so for the Alaskan cases, but yeah, this is maybe a longer discussion then. But yeah,
Right.
thank you for your response.
Okay, cool. Thank you.
Are there any more questions, or have we sated our desire to ask Tyler questions? I think that's probably the end of questions. It's after the hour too, Tyler. So I think we'll probably have to say thank you very much to yourself and to all the audience for yeah, as Paco has just put on the chat, a nice and interesting talk. It was great, really broad coverage of different techniques. So thank you very much indeed. Next week's seminar is our alternative time zone, 5 hours later than this one. So not good for Europeans, but great for those in the US and in Asia. So next week, the talk will not be chaired by myself, but will be chaired by somebody from the US. So Thank you very much indeed to everyone. Keep your eyes open for the announcement for next week's talk. But for those of us in Europe, we'll have to watch it on YouTube afterwards rather than in real time, unless we want to get up in the middle of our night. But thanks very much to everyone. And I won't close it down until Tyler's managed to get emails and things off the chat. But thanks very much to the audience and see you again soon.
Thanks, y'all.